Let us start solving homework 3.2, question 1. Suppose N of T is the number of supermarkets that are using a computerized checkout system, and you have an initial value problem. It says dN dt is equal to N times 1 minus 0.0005 N, and N at 0 at time 0 is equal to 1. Question says, use the phase line to predict how many supermarkets to adopt the new system, then sketch the solution. Before talking about the phase line, let us just introduce some new terminologies. First of all, an autonomous differential equation is introduced this way. Here you have dy dx equals to f of y. So on the left-hand side, you have the derivative, and on the right-hand side, you only have a function of y. You do not see any function of free variable x. For example, if you have y prime equals to 1 plus y squared, then you have an example of autonomous differential equation. When you have autonomous differential equation, what you can do, you can set the rate of change equal to 0 and find the critical points. Remember that in elementary calculus, to find the critical values, of a function, remember that when we are interested in finding the minimum, the maximum, we take the derivative of the function and set it equals to 0. So the same concept. We have the derivative of the solution and we set it equal to 0. This is what we remember. To find the critical values, set y prime, which is equal to f of y, equal to 0. Well, here by solving this equation, you can find some solution. The real value, like C, that satisfies this equation is called the critical value, or in differential equation terminology, we call it an equilibrium or stationary point. In differential equation, we call a critical value an equilibrium or stationary point. So why do we call them equilibrium or stationary point? Well, remember that you are setting your derivative equal to 0. The rate of change is 0. So you get stationary point. Since y prime is equal to 0. Remember that in elementary calculus, we had the following case. If you have a maximum or minimum, then at maximum or minimum, the tangent line was flat. M was equal to 0. You didn't have any movement at the maximum and minimum of the function. That's why we call them equilibrium or stationary points. So let us find the equilibrium or stationary points for this differential equation. These are the part of the process to form the phase line. Let us find the equilibrium or the stationary point or points. So we have the derivative. N prime is equal to N times 1 minus 0.0005 N, and we set it equal to 0. So one of the solutions is n equal to 0. The other one is 1 minus 0.0005 n equal to 0. So obviously one of them is 0. For the second one, we have to do a little bit of calculation. So 0.0005 n is equal to 1, or n is equal to 1, divided by, here you have 1,000. With 4 zeros, 10,000 divided by 5. So n becomes 2,000. We have two stationary points or equilibrium points for this differential equation. So these are the equilibrium for the differential equation, initial value problem. Very well. In our next step, we're going to use a vertical line to form the phase line. We use a vertical line. That vertical line is actually coming from your slope fields. Okay, let's take a look at our slope field. Let's go to our applet and visualize it. Very well. Here you have n, so let's convert n into y, and here you have n, which is y, parentheses, 1 minus 0.0005 times y, close the parenthesis, and let's see. I'm going to increase these to 3,000. Yeah, let me check. Very well. So here we have the slope fields for this differential equation. Let us take a look at the behavior of these curves. Take a look at this. As we are getting closer and closer to the horizontal line, where the line has slope 0 and is equal to 2,000, these solutions are converging to this line. Okay, continue clicking on your page and see the rest of the solutions, their behavior. As you can see, all of these curves are converging to n equals to 2,000. What about n equal to 0? So let me just move this a little bit here so we have more visualization. Let us add 3,000 so you can see. Very well. Around n equals to 0, the behavior that we see is not converging. They are diverging from your line n equal to 0. Very well. So what's the visualization? To simplify this graph, we use this phase line, the vertical line, and write it this way. So remember that that's your slope field that you have. This is your graph. Vertical line. N is equal to 2,000. Just move this a little bit down here. N is 2,000 and n is 0 here. Okay, very well. So as you saw, the behavior of your slope field is like this. Around this horizontal line, when n is equal to 2,000, remember that n is equal to 2,000, you have your equilibrium or stationary point. the rate of change is equal to 0 at n equal to 0 and n equals to 2000. Around line 2000, the rest of the solutions are all converging to this line. The rest of the solutions are all converging to this line. So this is the behavior that we see from the slope field. That makes sense. We expect this to happen. Also for n equal to 0, as you saw, the solutions are diverging from this line. You're going far away from this line. Very well. So it seems like the solutions are converging to the line n equals to 2000. Here you have a horizontal line, and no matter from above to below, from below to above, you see that they are getting closer and closer to this line. They're converging. Solutions are converging to n equals to 2000. However, solutions are diverging away from 0. Solutions are diverging away from 0. So you can use some arrows around 0 this way. So they're going away from 0. But this is your phase line. This vertical line is the phase line. So it says use the phase line to predict how many supermarkets will be eventually using this system. So take a look at this. As time goes to infinity, as t goes to infinity, the solutions are diverging away from none, it means that no supermarket, to 2000 supermarket are using this new system, because the solutions are getting closer and closer to this horizontal line, which is n equals to 2000. So since, I can answer this question this way, since the solutions are converging to n equals to 2000, it means that the limit of n while t goes to infinity is 2000. We predict that around 2000 supermarkets will be adopting this new system. Very good. Let us take a look at part B. Okay, let us erase this and write down part B. Part B says, now solve this differential equation and compare your answer with the one that you got from A, and how many companies are expected to adopt the new technology when t is equal to 10. So solve the initial value problem. Then visualize this, visualize the solution, and visualize the solution to verify the solution curve in part A. The solution curve in part A. And then how many companies you're expected to adopt the new system when t is 10. How many systems will be adopted? Companies will be adopting the system when t is equal to 10. Very good. Let's solve this differential equation. As you know, here you have a separable differential equation. So you get dn divided by n times 1 minus 0.0005 n equals to dt separable. And then take the integral of both sides. Of course, you have to use the partial fraction method. This is the integral of 1 over n minus 1 over n minus, here we simplify this to 2000. And here you have dn equals to t plus c sub 1. So we get ln of absolute value of n divided by n minus 2000 equals to t plus c sub 1, or n over n minus 2000 is equal to e to t plus minus e to c sub 1, or c sub 2. Very well. So what do we have? We have n equals to c e to t times n minus 2000. We're trying to just isolate n on one side, so you get n equals to negative 2000 c e to t divided by 1 minus c e to t. So this is the model that we have. We can just distribute this negative sign at the denominator, and we have negative 1 plus c e to t. Very well. Note that n is equal to 0. When t is equal to 0, n is 1. So 1 is equal to, here you have 2000 c divided by c minus 1. So c minus 1 is equal to 2000 c, or 1999 c is equal to 1. So c becomes 1 divided by 1999. Okay, so let's just plug those back into n. N is equal to, let me write n here, n of t becomes 2000 divided by 1999 e to t divided by 1 over 1999 e to t minus 1. So this is the model that we have. I can simplify this guy. N of t becomes 2000 e to t divided by, here if you take common denominator, we get e to t minus 1999. This is our model. So this is the solution for that differential equation. If we graph this solution, what do we get? Let us graph this function. The solution of the differential equation is just a function. Here you can use Desmos to visualize this function. So let's take a look at Desmos together. See what is our expectation. Do we get the similar solution that we expect by using the slope fields or not? So here we have 2000 e to power Let's just use t, or we can just use x for simplicity, divided by e to power x minus 1,999. So take a look at your solution. This is the solution for the differential equation that you have. That's the behavior of this solution. Now let us use t equals to 10 and solve for, and this is the graph that we have, so that guy is decreasing. Behavior is like this. Oh, it's like this. Let me just move this a little bit here. Okay, here we go. This is the graph of the solution that we have. Now let t be 10. What is n of t? N of 10 becomes 2,000 e to the 10 divided by e to the 10 minus 1, 999, which is, if you use our calculator, is around 1,834. So comparing this with the part A, comparing this value with part A, we saw that. Let us go back to check our slope field. This is your slope field. We expect that as t goes to infinity, n be closer and closer to 2,000. So the number that we got is pretty much close. After 10, we have 1,834 companies. So if you increase t to be 100 and more, then your number is getting closer and closer to 2,000.